Welcome back, everybody. This is another PowerPoint video presentation, and this will be the last PowerPoint video presentation that deals directly with how to program the PLC. This session we will talk about program control instructions. Program control instructions are used to alter the program scan from its normal sequence. Now, this can shorten the time that it takes the program to scan. Program control instructions optimize the total system response by executing certain routines only when required in the program. It's mentioned here. So, there are basically three that we'll deal with. Two of the three are referred to as override instructions. So we'll deal with the master control reset, which is what this PowerPoint is about. And then the next PowerPoint, we'll talk about the jump instruction and the subroutine. And you'll actually practice, mainly subroutine. That'll be part of your lab. You'll practice these instructions in your lab for Lab 5, your final lab. So let's talk about override instructions. They provide a means of executing certain section of the control logic if certain conditions are met. So these are all conditional instructions. They allow for greater program flexibility and they allow for greater program efficiency. And the reason they do that is because, well, this last point here, portions of the program not being utilized can be jumped over and outputs in certain zones can be left in their desired states. So we'll talk about the master control reset and the jump instruction as part of the override instruction group. And then we'll finish out by talking about subroutines, which to me are probably the most important of the program control instructions. So these operations are accomplished by using a series of conditional and unconditional branches and return instructions. They all operate over a user specified range or zone. The size of the zone is specified in some manner as part of the instruction, and that's important. How do you specify the zone or the size of the zone? And that's what we want to look at. But before we look at how to do that in software, let's look at an actual hardwire master control system. Now study this and notice that first rung. That first rung is actually not part of the program. The actual program starts on the second rung. That first rung is our master start and master stop, our master control relay. And if you look closely at it, you will recognize certain parts of the program. You'll see that this is just our old ceiling circuit, our start stop circuit that we talked about earlier and that you did the first lab over. You just to review, you have a normally closed push button. You have a normally open push button. When that push button that's normally open is closed, you have logic continuity through master stop. You have logic continuity through master start. And because you have, these are series, so you have a and an and so this output then, the MCR, is true. Since this output and that parallel contact, which is ORed with the master start, normally open push button, since this is true, that causes this to go true. Now remember, this is still pressed. This is true. When you release this, you no longer have logic continuity or power flow through the master start push button, but because this now is true, you have continuity through here, and it keeps this MCR latched down or locked on until you press the master stop. Now what is this coil controlling? Well, you'll see there's an MCR contact here and there's an MCR contact here. And you'll also notice it look kind of weird. Never before have you seen these vertical contacts. But you can kind of see how it works. Remember L1 and L2, those are the power lines. And so if this is started, this is latched, these are normally open. So when you push the start button, these will close and it'll provide power to the rest of the program. But what happens if you hit the master stop? Hit the master stop, then this MCR output here goes false. These contacts open up and it basically shuts down power to everything below those two vertical contacts. So you can see you can use this to provide input hour power shutdown of an entire circuit or portions of the circuit. So if you have an emergency shutdown, then you want to use this master control relay or master control reset, as we talk about it when we do it in software. Well, speaking of that, how would you implement this in software? And actually you can't. There's no way in the simulation software that you use or in the typical PLC software that you can get these. They don't make these vertical contacts. There's no way to do that. So how would you actually implement this? Well, there's, depending on the PLC instruction, there's always a way to implement the start and stop function of the master control relay or master control reset. So this particular method, and the one that you will use, is by using a start and an end fence. A start fence is just an instruction. It's an output instruction. It's conditional, and it tells the program where that zone, that we're going to call it the MCR zone, where that zone starts. And then the end fence, or the stop fence, it defines the end of that MCR, and that whole region between the start fence and the end fence, we call that the MCR zone. So look at this. If you look closely at this, you'll see that the start fence is conditional, as I said before. So this right here, when that's true, well, that's going to be true when you close that button. So when that's true, then this thing is on, and so the MCR instruction is true. Now when the MCR instruction is true, it's as if the MCR instruction zone is not even in there. So it acts like a regular PLC program that you're used to writing. This is ignored by the program. So this thing will run as normal. But if you turn this off, if that first rung of the ladder is false, then it will turn off the outputs. Not one, it turns all the outputs off, except for if you have a retentive output, like a retentive timer. If you have a retentive output, and there are some other retentive devices that we have not talked about, specifically latches and some solenoids. So if you have a retentive output, it will retain it in its last state. So if the last state, the output of that retentive device is high, it'll keep it high. If it's low, it'll keep it low. And that's usually not what you want, but we'll say a little bit more about that later. All right. So notice that, as I said before, that first rung of MCR instruction is conditional. The last rung is not conditional. And by not putting an instruction here before the MCR output on that last rung, then this rung is always true. You never want to nest these, by the way. You never want to nest MCR or make two overlap. You want to have, you can have more than one MCR zone if you want to, but they should be separate zones, separate entities. So the end rung is always true. Now, this is what I said before. When the MCR is de-energized, so when this is false, when it's de-energized, all non-retentive output de-energized. So anything that was a 1 in the input image table, it's reset to a 0 if it's non-retentive. When the MCR is de-energized, all retentive output remains in the last state. Now it's important that you understand that if you have a retentive output and the state, let's say it was a high or a 1 when you de-energize the MCR, then it's going to retain that 1. Now that's important to know, because when you start the machine back up, when you start the system back up, it's going to start with that retentive output as a high. And usually you don't want that for safety's sake. You usually don't want, when you turn the master power or master switch back on. Imagine your house. You know, at your house you have a main breaker. If you ever had power turned on, or maybe you had your electricity turned on in a new place where you move, the electric company always tells you to make sure that the breakers are in the off position. You don't want to have some machine like a fan or some unknown machine in the on position, and then when they flip the main power on, this thing turns on. You know, it can be a dangerous situation. I'll leave it to your imagination as to what can happen. So typically, you don't want to put retentive outputs in the MCR zone unless you really have a specific reason for doing so and you know what you're doing. Then I would highly recommend against that. And I think this slide deals with that, so I'll leave you to read that at your leisure. Now let's just kind of review what we talked about. The MCR zone is enclosed by a start fence and an end fence, and this terminology is used for the type of PLC that you're going to use. This is based on Allen Bradley, so they use the terminology start and end fence. But other PLC manufacturers will have something similar. The way they describe it or the name what might be different, but the functionality should be the same or very close. When the MCR in start rung is true, the program acts as if the zone did not exist. Program logic is normal. But when it's false, all outputs, all non-retentive outputs are reset, and that means they're set to 0 or turned off, and all retentive outputs are held to their whatever state they are when you turn the MCR from true to false. And that ends this first video. Now you will actually in Lab 5 you will deal with some of these instructions. So I think between this PowerPoint and then what you'll do in Lab, I think the information in here should be crystal clear. And these instructions are actually pretty simple, so I don't see or foresee you having any issues with them. So I'm going to pause the video for just a second, and we'll start up the second PowerPoint, and then we'll finish the lecture. Okay, well here is part 2 of program control instructions. This section, or this part, deals with the jump instruction and the subroutine instruction. So let's get started. In computer programming, sometimes it's desirable to skip over or to jump over certain parts of code, of your computer code. There was a language that I'm familiar with. It's kind of an old language called BASIC. In the BASIC programming language, each line or each statement, each instruction is given a line number. So let's say the first line of code was given a number maybe 1, and then you can go sequentially like 1, 2, 3, so forth. So let's say you had 100 lines of code, and there was a statement called the go-to statement. Let's say it was line number 10. So the program or the computer will execute each line sequentially, and when it got to 10, the go-to, maybe you had go-to line 75, it will skip over everything between line 10 and line 74. It will go to line 75 and pick up the program at line 75. So that's exactly how this first instruction, called the jump instruction, that we will talk about how that works. Then we'll talk about the subroutine, which of the two instructions, I think I prefer the subroutine. I think it's just more structured. I'm not a big fan of the jump. So the subroutine also allows you to leave the area of code where you're working to go to another part of the program and to come back. And so we'll talk about just a little bit about how that looks, and you'll learn more about that one when you complete Lab 5. So let's talk about some of the advantages of the jump instruction or jump command. First, like the other instruction that we talked about, reduce processor scan time, and the reason for that is you're skipping over parts of the program that you don't need to use at that particular time. If you did not have one of these program control instructions in your program, each rung of the ladder is basically read or scanned sequentially, whether it's needed or not. So by using a program control instruction like jump, if you know you're not going to use that portion of the program, why scan it? And that saves in scan time, especially if you have a really long program. The PLC can hold more than one program and scan only the program at a particular time, which can be an advantage. Imagine that maybe you have 4 programs on one long rung, and depending on the condition being met, you can jump to the first program or the second or the third or the fourth, again saving valuable scan time. Rather than scanning through one long program, you can divide the program up and only go to that part of the program or sub-program that you need to use at that particular time. Sections of a program can be jumped when a production fault occurs. As I said, I'm not a big fan of the jump instruction, but if I were going to use it, this is the reason I would use it. So sections of a program can be jumped when a production fault occurs. So what you could have a sensor or some kind of a switch, monitor, some kind of procedure, and if it's mapped to a bit position in the input image table or the data table, let's say when a fault occurred, you had your program written so that the input image table is updated to a 1 in a particular bit condition. Well, that could be the conditional bit that makes this jump instruction true, and then you can jump over part of the code or part of the program, or jump to part of the program that's necessary to address that fault condition. So that would be one reason I would use this jump command. If it wasn't that, I probably would prefer the subroutine. But that's a matter of personal choice. By the way, pretty much every PLC will have a jump instruction. It may not be called jump. Some PLCs will use the term skip, but the skip instruction and the jump instruction, for all practical purposes, they're exactly the same. So how does a jump command work? Well, here we have a program, schematic of a program, and this program is scanned sequentially, and you see there's on one of the rungs there's a jump instruction, and then there's a destination to which you're going to jump. And so what happens is this scan, as I said, sequentially, you reach the jump, you're taken out of the normal program flow, and then you jump all of those rungs and you land here at the target or the destination. So anything between the jump and that jump destination is skipped over, and then the rest of the scan will continue as normal. Well, how do we do that? How's that done in the simulation software? How do we implement that? So in your simulator, and most PLCs will have some system or some way of doing this similar to what I'm going to show you here. In your specific PLC, the jump is used as a pair. You have the jump, and that jump is jump to label. The jump is short for jump to label. So you have the jump and you have the actual label. Now notice the jump is conditional. So when input A, whatever that is, when that's true, then the jump instruction goes true. It has logic continuity. And then so what it's going to do is look for a target. Well, the target is the label. Now notice they have the same address. 01 here, 01 here. So it knows, it matches or marries this jump instruction with that particular label. You can have multiple jumps in the program, and the way the instruction knows where to jump is by matching the address of the jump to label with the actual address of the label. So these numbers will always match. Point is, anything in between the jump instruction and the label instruction, anything in between that, you'll skip over. Notice that this is non-conditional. Just like with the master control reset, that last rung is non-conditional. So here's a more concrete example. Here's a code, and this is the way you'll see it in your simulation software. So here we have the conditional input A that controls my jump. If this is false, then the program will run normally in sequential order. If this is true, then this jump has a address 20, which is the address of the target label, and so it'll jump to 20, and anything in between this jump instruction and that label instruction, all those rungs are skipped. But notice something, this one actually has two jump instructions. You can jump multiple times. This is also mapped to that label. So let's say this input never went true. it'll scan sequentially, and if the input D went true, then it'll skip this rung right here and go directly to the label. So the point of this is you can have multiple jumps. You can have multiple jumps. You can also jump backwards in the program. However, I highly discourage doing that. It's not a good thing to do. If you jump backwards, and I would be careful, you never ever ever want to jump into an MCR zone. That's a no-no. So never jump to MCR, and if you're going to jump backwards, limit the number of times that you jump backwards. Jumping backwards can be a maintenance nightmare if you have a really long program. Okay, another one, and my favorite, is the subroutine. Now, every programming language has some kind of subroutine. Sometimes they'll use the name subroutine. Depending on the language, they might call it a procedure. In some computer languages, they call it a function. They're all the same. Basically, a subroutine, a procedure, a function, what they are individual small programs that can run independently of the larger program. And the subroutine, the way it's done with the PLC, you actually will go out of your main ladder file and you'll go to this small secondary file, which is called the subroutine. You'll run that program and then you'll return to the actual main program. Now, I really like that method, or this method, and the reason is, since the subroutine itself is a program that works regardless of what's happening around it, regardless of what's happening in the main program, you can do a couple things. Number one, it makes maintenance really easy. If you need to change something inside the subroutine, you can change it, and since the subroutine runs independently, you don't have to worry about it affecting other parts of the main program, which can be a huge thing if you have a really long program. Another reason that I like it is this ideal in computer programming or computer science. There's something called reuse. And reuse basically is just what it implies. So you can take a code or program and use it in another program. One example of that is I can show you here on the computer if I can move the screen. So if I bring the screen up, this little let's see if I can, this little X button right here, or any of these buttons at the top of your screen, when you use Microsoft products, you have a little X button, and you're familiar with that. You know that if you hit that button, it'll close the program. Well, that button is actually programmed to do a certain thing. And notice they use the same program in Microsoft Word and Access and basically all of Microsoft products. You only have to write that code one time, and if it's a subroutine, you can actually use it in other programs without having to rewrite it. And so that X button, or the close button, they call it an object in computer programming, but they wrote the code one time and they use it in all of Microsoft products. And so this idea of reuse, while it might sound kind of simple, is actually big to be able to reuse certain parts of the code. But there are other advantages also that we won't go into. When you use the subroutine, there's actually 3 subroutine related instructions, and here they are. There's the jump to subroutine, there's the actual subroutine, and then there's the return. Now the jump to subroutine is what goes in the main program. The subroutine and return, these are actually part of the actual subroutine. Now the way this is going to work, and I actually take you step by step through how to create a subroutine so you can apply this to your Lab 5. But you're dealing with 2 windows. You're dealing with the main window that you're familiar with, where you create your actual ladder run, your program edit window. But there's also a second window, the subroutine window, that when you double click on it, opens up another set of rungs where you can put your subroutine. This jump to subroutine will go on the main ladder. Now notice there's a U:20. That's the address of the subroutine that you want this to go to when this jump to subroutine becomes true. So let's talk about a little bit about these instructions in a little bit more detail, and then we'll look at an example. JSR, the jump to subroutine, causes the processor to jump to a targeted subroutine file. This is the decimal numbers of the file. Now make sure you look at the footnote here, and you'll see this when you actually do the lab, and then you'll see it here later on in the PowerPoint. The subroutine serves as an identifier that program file is a subroutine, and basically it matches the subroutine with the jump to subroutine label. And then the return is the instruction to leave the subroutine. If every condition has been met in the subroutine, it will leave the subroutine and then go back to not to the jump to subroutine statement, but to the one that follows it. Let's look at an example of this. Oh, by the way, it says that return is automatic at the end of file if this instruction is omitted. In other words, you can leave this instruction off and it'll still return to the main program. However, you don't want to do that. I will highly recommend using every instruction, just so if another person looks at your code, it makes sense. It's logical. So even though it probably will work if you left that off, it's not a good idea to do that. So here's from a large view, high-level view, how the jump to subroutine works. You have two rungs. This is the one that you're used to creating, this main rung. But then there'll be a way to create a little sub program or sub rung, and you'll write that program. In the main rung, you'll execute this. It'll scan this sequentially. Notice the jump to subroutine is conditional. So if this condition is false, it'll just go right past that. Nothing will happen. But if this condition is true, then you'll actually jump out of the main ladder, the main program, and it'll come to the subroutine that has the same address or that's mapped to this JSR instruction. So you'll jump out of the main program, you'll execute the subroutine, and then when that subroutine is complete, you'll go back. Notice you don't go back to the same rung. You'll go back to the rung that follows the JSR instruction, and you'll continue with the program. So this is a really, really, really good way of programming and keeping your program organized. Not so much if you have a small program, but if you have a really long program, then I think subroutines are the way to go, and they're my favorite by far. So how do you set up a subroutine? What's the procedure for setting up a subroutine? So I have that note ladder location where subroutine should be called. That is where you're going to have the jump to subroutine start. You create a subroutine file for each location. Each subroutine file should begin with the subroutine instruction. Actually, it won't work if you don't do that. So at each ladder location in the main program where the subroutine is called, you want to add a jump to subroutine or JSR instruction, and specifying the subroutine file number. That's that number that I showed you that I called an address on the example here. That would be this file or that number. So actually, here's an example that we'll talk about, and then we actually go through. I go through step by step. Went through and actually built one for the purposes of this video. It will take you step by step through how to set up a subroutine, and once you do it one time, you'll see it's a piece of cake. It's pretty easy. But this PowerPoint will take you through it, and then you can, if you view this before you do Lab 5, it'll make things a lot easier. Here's an example. Now I didn't have a lot of real estate here, so this is actually, it looks like one long rung, but it really isn't. Imagine that you couldn't see here on the bottom. This is a totally different file. The top one is my program file, my main rung. And then this smaller one down here, that's the subroutine. So notice this says it's file 2, this is file 3. You'll see what that means when you get to your simulation software. But going through this, for this particular example, the jump to subroutine is the first rung, the first line. But probably it wouldn't be. I mean, it could be, but probably it will have some code above this. Anyway, when you get to this line, there's a sensor mapped to the first rung, and so as I said before, that jump to subroutine is conditional, and so when this sensor goes true, I have logic continuity, we're going to jump to a subroutine. But how do we know which subroutine to jump to, which file? Each subroutine is kept in its own individual file. Well, here's the address or the file number. So this is file number 3. And notice the subroutine down here, which if you imagine this is somewhere else, you can't really see this. Look at that. That's file number 3. So when this run goes true, we're going to jump to subroutine file number 3. We skip over all of these rungs and we go right to the subroutine. And then we go into the subroutine. We run whatever code is in there. In this particular one, we have a timer, an on delay timer, a couple timers in here. And so whatever the code is, we'll run that code in the subroutine. But then when we hit this return, we'll return not to the rung with the JSR. We'll return to the one that follows the JSR, and then the program will continue to run as normal. So pretty simple. So here's a step by step, and again, I'll just kind of click through this so you can see it. And I recommend maybe going through this PowerPoint. I'll put it on Canvas, and you can go through this part of the PowerPoint and just kind of click through step by step, and it takes you through the steps that you need to create a subroutine. And when you create the first one, any one that you do after that will be pretty simple. So here I start and then take you step by step through it. So I won't read this. You can just kind of follow this when you do your lab, and you'll see how easy it is. Here for your simulator, you have file 3 through 9 of your subroutine files, but a actual PLC could have many more. Double clicking on one of these opens up that subroutine window. And this is what it looked like when it's open. You double clicked on that, it opened up a new window, and now you're able to program your subroutine. So as I said before, the procedure for creating a subroutine is very simple. So again, I recommend just having the PowerPoint open, just kind of click through and do what I did here in the video, and then once you go through it one time, then I think the lab will be a piece of cake. So that's it, and this is actually the last, as I think I said before, this is the last PowerPoint we'll do that deals with programming directly. I think we have 2 more PowerPoint presentations. One will be on output devices, and that'll be in a couple weeks, and then we will have the final one, which actually the exam, one of your exams, will be part of a research project. I'll tell you more about that one later. That ends this video, guys. Have a great rest of the day, and we'll talk soon. Thank you.